Hello everyone, welcome to lesson 80 of our Golang code. In the past lessons, we have gone over various concurrency primitives in Go. We went through them to build our base, and now is the time to take a step further. This lesson will look at the concurrency patterns called pipelines or data pipelines. For this, I will be drawing heavily from a Go Teams blog on streaming data pipelines. You can find the specific article linked in the video description. This lesson will have lot of coding, so it might be a bit longer. We will be diving into real-world examples presented in the blog to solidify our understanding, so let's get started. First, let us go over why we need pipelines. Let me ask you a simple question. Why do we write functions, methods, etc.? The answer is that they help us abstract different areas of code by dividing our code into code blocks where each function or code block is responsible for performing a particular task. This is the basic concept behind pipelines. Pipelines consist of different stages where each part of pipeline or stage is responsible for performing defined operations. Data goes from one stage to another. Then the question arises, how does this help us? The answer is, having different stages in pipelines where each stage is independent of any other stage allows you to modify them without worrying what impact it will have on other stage in our pipelines. Since we are talking about concurrency, how does data pipeline sit in the concurrency world? The answer is that streaming pipelines can make use of I/O and multiple CPUs available, increasing the performance of the operation. Here we have a flow diagram depicting a simple pipeline. Here first stage is the generator stage. That is, it will take some data and put it on a channel that can further be supplied to the multiplier stage. Multiplier stage will take data from the channel to multiply it with a provided multiplier. Then the final stage is outputting the data. So this stage could be dependent for outputting data to the console or writing to a file. In more general terms, a pipeline could consist of multiple functions. For example, one function takes a slice as an input, doubles each element in the slice, and returns the slice of the double elements. So that's the basic idea of a pipeline where you have multiple stages. Here we have 3 stages to our pipeline, and they are all interconnected. Just like a pipeline in real world. Data from 1 will go into 2, from 2 to 3, and out. Now let's discuss pipelines in context of Go. In Go, a pipeline can be visualized as a series of interconnected stages where each stage consists of coroutine executing the same function. Data flows through pipeline. Each stage receives value from its predecessor via channels, performing operations on the data, and then sends the transformed data to its successor stage using channels. As we discussed in the example, please note that except for initial and the final stage, which only have one inbound or outbound channel respectively, each middle stage can have multiple inbound and outbound channels. This setup allows for complex data transformations and parallel processing within the pipeline. In the wild, you will see 2 major types of pipelines. One that performs batch processing, that is, takes a collection of data and returns a collection of data after processing. Then the other one performs stream processing. That is, processing and emits one element at a time. The one we write using channels is a streaming pipeline. If you would have used a slice or an array, it would be a batch processing pipeline. Now with Go's concurrency model, it becomes really easy to perform tasks in a pipeline stage concurrently. Channels are great for feeding data to a pipeline stage and provide the processed data output from the pipeline stage. Usually a pipeline pattern using channels starts with a generator stage that takes data and puts the data onto a channel. Since each stage uses channels that are concurrency safe, you can utilize concurrency to gain performance. Also, each stage does not have to wait for all values from previous stage. It can process values as it gets them. As such, the name stream processing when using channels. Now with the basic concepts clear, let us start with a small example of 3-stage pipeline. So let's write some code. First, I am going to create a gen function or the generator function which takes periodic parameter of nums, which are ints, and returns a channel. The gen function puts all the numbers provided to it on the channel. Func gen takes num. Inside it, let us first create our output channel. then simply just return it. Now let's write the code that actually puts the nums on the channel. We will start a new Goroutine to do this. We range our nums and put the values onto the out channel. At the end of iteration, we will close the out channel. So that is here the generator stage. Now let us write the second stage, which is a squaring stage. This stage will take values from the input integer channel and write the square of integers to a output channel. Func_sq takes a read-only channel of integer values, returns an integer channel, again a read-only channel of int values. Inside the sq function or our squaring stage, let us create a output channel. Again, let us just return the output channel. Now to square the values from the input channel, let us create a Goroutine. Inside the Goroutine, we will range over the input values picked up from the channel and put the squared values onto the output channel. So here, we just range over the values provided by the input channel. Write to the output channel, that is n into n over the squared values. Then after we are done, we will close the output channel. So these two here are our two stages. The first stage generates the values, that is takes an input slice and then puts a value on a channel, returning the channel. Then we have the second stage, which takes an input channel, reads value from it, and writes the square of numbers to the output channel. Now our final stage, which is printing the values. We will write that in our main function. First, let me get a channel of our provided value so I can use the generator stage. Let me say 2, 3, 4. C here is the return channel, so I can do out and then square, provide the C channel, that is our input channel for square. Then let us range from values provided by the output channel. We are just going to print it. So that forms our 3-stage pipeline. The first stage, generator stage, then the square stage, and then the printing stage. Now let us run our program to see the output. And as you can see, we were able to get 4, 9, and 16 printed to the console, which are again square of values 2, 3, and 4. So that's it for our first example. Now let us explore another pattern, which is fan out and fan in. We will be discussing this in detail in a future video. For now, let's just go over an example. So when we are using channels, multiple functions can read from the same channel until the channel is closed. This is called fan out because each function will read available set of values, thus dividing our work. So this provides a way to distribute work amongst the group of workers in a parallelized CPU use and I/O. Now we can create a function that can read from multiple input channels, proceed until all are closed by multiplexing the input channel inputs onto a single channel, which is finally closed when all input channels are closed. This is called fan in. So basically, fan out is distribution of work and fan in is collecting the work together onto a single channel. To demonstrate this, for fan in, we are going to create a merge function. The merge function will take multiple channels and put the values from these channels onto a single output in channel. So let's code our merge function. As we discussed, the merge function is going to take multiple input channels. So here we are accepting a slice of channels. The output is a single in channel, which is read-only. So let's first create our output channel and then return it similar to what we did in our other stages. Now what we are going to do is create multiple Goroutines to read from each channel and then write it to a common output channel. So let's define the output function first, which we are going to start in a Goroutine. The output function is going to take a single int channel. Then we are going to range over the values provided by the channel and then simply put it onto the output channel. To manage the Goroutines, we are going to use a wait group. So let me create a wait group variable, sync.waitGroup, and then since we are going to start the output function in the Goroutine, let us call done after we have read the values from C and written them to the output channel. So wg.done. Now the number of Goroutines we are going to start is equal to the number of channels. So let's add the number to the wait group. Now let us range through the channels provided to us to create a Goroutine from each. Inside it, let us create a Goroutine. So we are going to do go output and then provide the channel. Now in a separate Goroutine, we are going to perform the wait operation. That is, waiting for the operations to be completed. And inside, we are just going to do waitGroup.wait and then finally close the output channel when all Goroutines have exited. So this here is our merge function. To revise, we are taking a slice of n channels and returning a single n channel that will combine the values from each channel onto the output channel. Inside it, we have our output function, which does the same. That is, takes the value from a provided channel and then write it to the output. Then we start each coroutine for the provided channel, and finally we wait for them to be completed, then returning the output channel. This way, we are merging from multiple input channels the values onto a single channel. So let us now perform fan in and fan out. Here I'm going to rename this variable to be more clear, that is input. So we have our input channel. Now let us create two squaring stages, C1, C2, square. I realize we are using a reserved keyword. I intended it to be updated to n. Now back to our example, we are getting C1 and C2 returned from calling square 2 times, providing the same input channel. That is, we are dividing the work between two functions or two Goroutines. Now, instead of ranging from out, we need to merge the return results from C1 and C2. So we are just going to do that. Call merge and then C1 and C2. So that's it. Here we are doing a fan out, that is dividing the work between two Goroutines. Then with merge, we are doing a fan in, that is combining the values from two channels into one. Now let's run our program to see the output. Go run main.go, and as you can see, we are still getting the output we expect, that is 4, 9 and 16. In our previous lessons, we have learned that we should always ensure that coroutines are cleaned after. So there are multiple instances of coroutines that can hang in our code. To make sure we are cleaning after, let us add the done channel. First, let me update the gen stage to react to the done channel. And then let us move this up to say therefore close the output channel. Inside the for loop, let us create a select statement to write to both the output channel and listen to any signals on done. This is the first case, that is writing to the output channel. Then the next case is listening to the done and then return. We have made the generation stage use the done channel to clean after the coroutine that we create. Similarly, we are going to update the square stage. Similar to what we did in the gen stage, let us update the loop with an select statement. This is our first case, and then case where we listen to the done channel and return. Now to ensure that out is always closed, we are going to defer the closing of out at the beginning of our coroutine. So we move it up and say defer close. Similar with the merging stage, move the waitGroup.done to before the range and therefore calling of it. Inside the range, we create a select clause. As usual, this is our first case, and then the next case is listening to the done channel. And if there's anything, we return. We don't use the done channel here because this is used to do what done channel is already doing, that is closing out the output channel. Then in our main, let's create the done channel, therefore close the done channel, and then pass it to all our stages. Sorry, I used clear where we should be using close. So we have modified our code to react to done channel, that is we are cleaning after the coroutines that we create. Now our pipeline will close successfully. So just to revise, stages close their outbound channels when all the send operations are done. Stages keep receiving values from the inbound channels until those channels are closed or the senders are unblocked. So that's a demonstration of using pipelines with coroutines. Now let us move to a bigger example. For this, I'm going to remove everything that we have written here. In this example, we are going to write a program that takes a root directory path and then prints the digest, that is a MD5 digest for each regular file under the directory, sorted by the path name. In our first iteration of the program, we are just going to write the program to not use concurrency at all. So let me create a function MD5 to perform this operation. We take a root or the root path. Our MD5 all function will return a map where the key is a path to the file and the value is the MD5 digest. So string, which is the path, and then the type for MD5 digest, or an error in case we fail to traverse or create a digest. First, let us create the return map. Now let us traverse the root path that we have been provided with filepath.walk directory function. So error filepath.walk directory. As you can see, walk directory walks the file tree rooted at the root, calling function for each file or directory in the tree, including the root. So we are going to provide the root directory or the root path to it, and then a callback function. Inside the callback function, which is called for each directory or file in the current path, we need to process the provided inputs. First, we are just going to check if there's any error, and if there's one, we are just going to return it. Then for our function, let us check if D is a directory. If it is, we are just returning nil, that is skipping the rest of the processing. Now let us read a file and create a digest of it. os.read file, provide the path. If error is not nil, return error. Otherwise, use the data that we have to create the hash. Save it into the map md5.sum, provide the data. So this line here essentially is saving the digest to the path in the map. Then indicate that we don't have any error by returning nil. That's the implementation of the callback function. Now if there's any error in the walk directory function, let us return it. Otherwise, we return the map with nil, that is no error. So that's it for our MD5 all function. We are taking a root string, then traversing over the directory using the walk directory function. And finally, we are writing the digest in the map mapped to the path of the file. Now let us call this function to actually print it. Map or error, return from calling MD5 all. The root path is going to be from the command argument. So we are going to use os.args and just accept the index first element. If error is not nil, we will print the error and exit. Otherwise, let us get the path from the map. Range over the map to get the path and store it into the paths slice. Here we need to update it to be a map so that we are only reading over the keys of the map. Then we are going to use a sort package to sort the paths, and finally we are just going to print the MD5 digest of each. First is the digest and the second is the path. Now let's create some files so that we see the digest printed to the console. Now let's run our program to see if it works. Go run main.go. We need to provide the path or the root directory. So let us provide the current directory as the root. Go run main.go dot, which is the current root directory. And as you can see, we got the MD5 sum or digest printed to the console along with the file path. Now let us write the same program to use concurrency by implementing all the techniques we have learned in this lesson. We are going to divide the whole process into two stages. The first stage will get all the files from the directory and create a digest for each file in a new Goroutine. Results will then be sent back on our output channel. Let's remove all the code from here. Start over. First, I'm going to create a result struct to couple together the result and error if there are any. Type result, which is of type struct. First field is path, which is a string. Then the digest itself, which is sum, and error if there's any. So this result struct will hold our result for our walk. Now we are using channels to return the result and a separate channel to return error from walk directory. So this could be confusing why we are coupling the error in the result struct and if why we need another channel to send back errors. So the error that we are coupling here is any error when we actually go to create the digest. The one that we return on the error channel will be any error that we encounter during the walk of our directory. Let's write our function sum file, which takes a done channel, then the root directory path returns a channel which is read only and has results, and then another channel of error. First, let us make our channel of results, then the error channel. Now let's create a Goroutine to perform the walk. Before I do that, let us make the error channel a buffer channel so that we don't block writing to it. Inside our Goroutine, first we are going to create a wait group. because we are going to create each coroutine for creating a MD5 hash or sum for each file we encounter. Sync.wait group. Now let's start our walk. Filepath.walkter root, then our callback function. Let me just close the side panel so that we have more room to display our code. Now inside the callback, let us first check for any errors. If there are any, we return the error. Next, let us check if it's a directory. If it's one, we just skip over it and return nil. Now let us create a new Goroutine to process the file and create a digest. So for each, I'm going to do waitGroup.add 1. Now a new Goroutine to create the digest. Similar to what we did before, data or error after reading the file, select statement. First is the case of writing back data to the channel path, which is the provided path, and then sum, which is the MD5 sum, or the error if there is one from reading the file. And the second case is again reading onto the done channel, then done. Basically, we are creating each coroutine from the file path provided by walkter, and in the coroutine, we are creating the hash, sending over the results back on the results channel. What we should do here is just return and then move our wd.done to a defer statement. Now to handle the parent coroutine, that is this one here, let us create another select statement. Let me scroll this up. First case is that we listen on to the done channel. If done is called, we will return error saying walk cancelled. The default case here will be returning a nil error. So now both our Goroutines have been handled carefully. Then let us create a separate Goroutine to wait for the completion of all the Goroutines that we start here. Similar to what we did before, wd.wait and then close the output channel. Finally, let us write the error to the error channel and then return both the channels. Just to be sure, let us just check before writing to the error channel. So that's it for the code in our sum file functions. Just to recap, we are accepting a done channel, then a root directory path. Returning from the function, we have a result channel or error channel. First, we make the result channel, then the error channel. Then we start a new Goroutine to perform the walking. Inside walking, for each file that we encounter, we create another Goroutine to get the digest or error. After calling that, we create another Goroutine to wait for all the Goroutines that we started here to be completed and then close the output channel. And if there's any error during the walk, we write it to the error channel. Finally, we return the output and the error channels. Basically, we are utilizing concurrency to process creating of digest in a more performant ways. Now let's write our MD5 function again. MD5 all takes a root string. Similar to what we had earlier, returns a map where key is a string or the path name and the value is the sum. Inside it, first let us create a done channel, call the closing of done in a defer statement. Now let us call the sum files function. Provide done and the root directory. To create a map from the provided outputs, let us first initialize a map of string keys and MD5 digest values, size is 0. Now let us range over the channel provided from some files. First, let us check if there's any error on the result channel. r.error not is equal to nil, return nil map and r.error. If there's no error, we create an entry in our map. r.path is equal to r.sum. Then let us check the error from the error channel. If there's error, we return it. Otherwise, we return the map that we created along with a nil error. What MD5 all is doing here is just collecting the results from the Goroutines that we created here and putting them into a map. Now the main function will be very similar. First, we call MD5 all, passing in the first argument, that is args. If error not is equal to nil, print the error and exit. Then we create paths, which is a slice of strings. Append all the paths from the map provided to us. Before printing, sort them out, and then print each digest with the path. So that's it for our code. Now let's run the program to see the output. go run main.go, provide the root of the directory, we encounter a deadlock. That means we are not handling Goroutines carefully at some place. As you can see, it points to line 74. That is when we are reading from the RC channel. So let's go back. When we write to the RC channel, we only write when there is no error. We perform a similar check when reading from the RC channel. So that means we can remove it and make sure that there's always a value on RC to read from. Save it and let's run our program again. And as you can see, we got the digest printed along with the path name. So our code now uses concurrency to process the sum of files in Goroutines. But there is another optimization that we can make. Notice that we start a new Goroutine for each file that we find during the walk-off directory. But this is something that could consume a lot of our resources, so we need to limit it. To do that, we are going to divide our MD5 into two stages. The first stage is going to read and return all paths, and the next stage is going to create digest from these paths. So here I'm going to update this to say walk files. First, we are going to modify our return channel to just be a channel that holds string, which will hold the paths for each file found in the directory. Paths is a channel that holds string values. We are not going to create a new Goroutine for each file that we find, so we don't need the wait group here. Similarly, we don't have to wait for all the Goroutines that we create. Let's also modify the signature of function to return a string channel, which will hold the paths. Let's remove the Goroutine that creates a digest and just write back to the path channel the path we are iterating over right now. So I can say path and then pass the path. Then return nil to indicate that there was no error during the walk. Let's update the return of walk files to return the paths. So that's it for the walk files function. We modified it to now return paths channel and a error channel. Inside it, we just create a Goroutine that starts the walk and returns all the paths from the walk. Or if there's an error, returns the error. Now let's create a digester stage that will create the digest from the provided path. Func digester. First, as always, is the done channel. Then we'll take in the path channel. Instead of returning a channel for results, it will just take a read channel, which will just be used to put in the results that can be used by the caller to read from it. So we will take a channel C, which is a channel that is read only and holds the results. Inside the digester, I'm just going to range through the paths provided by the path channel. Then we read the data using os.read file, provide the path. Now let's create a select statement to write the results and also listen to the done channel signal. First case, writing the results back to the result channel, path sum, which is MD5 sum, provide the data and error if there's any. Second case is again listening to the done channel. In that case, we just return. So that's our digester here. What it's just doing is take the path channel, read from the path channel the path of the file, create the sum and return it. It is returning the results using the path and C channel, all the results channel. Now to limit the number of coroutines that we create for digesting the files, we are going to use MD5 all. First, let us update to now be a path channel. Instead, we are doing walk files. So the walking operation returns the paths on a channel or error if there's any. We will pass the path channel to the digester. First, we need to create a limited number of Goroutines that will create the digest. So we are going to synchronize using wait groups. For starters, I am going to create 20 Goroutines to create the digest. Here we are starting a for loop to create 20 digesters in a Goroutine. Inside the Goroutine, we call digester, passing the done channel, passing the path channel, and the results channel. We need to create the results channel, so let us create one. Now in the Goroutine, let us call the wd.done in a defer statement. So here we are creating a limited number of digesters. Then we need to wait for all the Goroutines that were created when we were creating digests. So to do that, I'm just going to create a new Goroutine. Inside the Goroutine, like we did earlier, we will wait and then close the results channel. Everything else remains the same. We just need to update it to now read from the results channel. So that's it for our code. Let us run it and see how that goes. Go run main.go, provide the root path. As you can see, we got nothing printed to the console. So there's something wrong with the code. Let's analyze it. So I'm just going to ensure we are closing all the channels. We have the path channel, we are writing to it, but not closing it. So that means when we are ranging over the path channel, we will get stuck here. That's a problem that we have. So we should call the closing of the path channel in here with a def statement. That's it. Now let's try to run our code again. This time we have another problem. It's saying that we have negative weight group counter. That means we messed up with our weight group. We are using weight groups in MD5 all. Oh, and as you can see, we forgot to add the number of digesters that we want to start. So we should add them here to the weight group. Now let's run our program again to see how it goes. So as you can see, we were able to get the results printed to the console. As we saw, it is important to remember to close all the channels we are writing to, or the owner of the channel should close the channels after the operation has been done. Another thing we noticed was to always use weight group properly. That is, don't forget to add or don't forget to call done after the operation is completed. Just to summarize what we did here, we created a walk file stage which takes a root string, starts a Goroutine to walk the directory from the root. Then we generate the paths of each file in the directory and put it on the paths channel. We write the error to the error channel, and then in the end we return the paths and the error channel. In digester, we are simply taking the paths channel and a results channel. We iterate over the paths channel values, read using the os.read file, and then output the results on the results channel. Then in MD5 all, we bring everything together. First, we read the paths using walk files. Then we create a certain number of digesters, which is 20 in our code. Create the digesters, pass the done channel, pass channel, and the results. Then we wait for the digesters to complete their operation. Finally, we create map from the results. And then in our main function, we are just sorting and printing the output to the console. So as you can see, there are 4 stages to our pipeline. First is walking the files, then the digester, followed by MD5 all and the main function. So this is how you can use concurrency and the pipeline model to write efficient programs. So in this lesson, we studied the pipeline concurrency pattern, which is very useful along with the concurrency model that Go supports to perform operations concurrently. It helped us gain performance by using Goroutines and channels in the pipeline stages. That's it for this lesson. I hope you liked it. If you have any questions, please post a comment under the video or reach out to a Discord server. Until next time, happy coding!